All right, greetings and salutations. So in our previous videos, we were dealing a lot with propositions, which are statements that are true or false. And today we are going to get into our last topic before we actually get into methods of proofs, which I know is everyone's favorite, right? Proofs, yay. But yeah, before I explain what exactly predicates and quantifiers are, uh, let me give some motivation for it. So before we were dealing a lot with propositions like statements like one is an odd number. This is a statement that is either true or false. In this case, it's true. Two is an odd number. This is a proposition with a false truth value. But what about the statement x is an odd number? Well, now this isn't a proposition anymore. We don't know if it's true or false. That depends on what value the variable x takes. So x is a variable, right? That means this is not a proposition because it's a free variable. We call it a free variable where there is no actual um, instance associated with it. There is no number associated with it like one or two. So what we call this third sentence is not a proposition, but a predicate. So we can actually label predicates just like we do propositions. So we called them P and Q before. Let let P of x let P of x be this statement right here. X is an odd number. So notice that instead of just P, we have P of x. It takes in x as a parameter, takes an x as an argument, and spits out a proposition. So once you plug in a value for x, then you get a proposition. So this P of x is a predicate. It is a function that takes in an argument and spits out a proposition. And this argument um, is over any domain of our choice. In this case, we want to restrict our domain to be the set of counting numbers. A set is simply a collection of things. You could think of it like a bucket of things. It can have 5 things in it. It could have 10 things. It could have no things, or it could have an infinity number of things. It's just a bucket of things. So we want to restrict our set, the set of values that x could take, to be over the counting numbers. So we have a special name for it. We write it like this fancy n. This is known as the counting numbers, or we call them the natural numbers. So natural numbers. So you want x to range over the set of natural numbers, which is just, you know, 0, 1, 2, and so on, all the way through infinity. Now, some say that 0 is a natural number, some say it isn't. I don't want to start any wars in the comment section, so I'm not going to give my personal opinion on it, but I'm just including 0 because, often in computer science, we start with zeros. We start our array indices with 0, and everything starts with 0. So that's why I'm including 0 in this. But yeah, we want x to take a value 0, 1, 2, 3, 4, and or so on. So once we plug in a value for x, say that we have p of 3, we plug in 3 for x. Now this is a proposition. Now that we plugged in a value for x, this is the statement: 3 is an odd number, and that is a proposition. So another way we could make this statement with the variable into a proposition is by modifying it like this. Oftentimes in math, we will actually, let me just write it out first. So we could say for every natural number x, x is odd, right? We can write this statement right here. Now, even though x is a variable still, it is bound by this quantifier right here for every natural number x. So x is, we are saying for all the numbers in this set right here, x is odd. This becomes a proposition because now this variable is no longer free. It's no longer just floating off in space by its own. It actually is quantified. It's saying x is every natural number, or like we are considering every natural number. We can also write another type of quantifier, or such as, the other quantifier we will go over is there exists a natural number x such that x is odd. Now, again, x is still a variable, but it's bound by this quantifier. We are saying that x is some natural number, right? There exists some natural number x such that x is odd. So again, our domain is that we are considering x to be part of is the set of natural numbers. So these two become propositions. Now, this first one, for every natural number x, that is called universal quantification. So instead of for every, you can write for all or every. It doesn't matter. How we write it is like this upside down a, it means for all or for every. So we can write for every x in the natural numbers. This e sign means is in or is an element of. So for every x in the set of natural numbers, that's the same thing as saying for every natural number x, for every x in the natural numbers, x is odd. That's the same as this first statement right here. Now, for there exists, we write a backwards E. So this backwards E means there exists an x in the natural numbers such that x is odd. Now, clearly, this first proposition is false because we can provide a counterexample. It's not true that every x is odd. Say x is 4. 4 is not odd, and 4 is a natural number. So this is false. And this second proposition, there exists x and n such that x is odd. Sure, we can choose such an x as well. We can say x could be 1, or x could be 5, x could be 11. So this is true because there exists some x. At least this exists x means there exists at least one x. For all x means every single x. So every single natural number is odd. So that's existential and universal, or universal and existential quantifications. And oftentimes we will deal with statements in math like these. We will want to quantify over our domains, whether it's natural numbers or anything else. Like natural numbers, just one example of a domain we want to talk about. So let me give another example, right? We don't have to restrict ourselves to just one variable, like p of x. We can have, let's create another predicate. So let's call this predicate legs. This is the name of our predicate, and it takes in two variables, x and y. And we want to say X is in the set of all animals. So let animals be a set of the set of all animals, and then let Y be in the set of natural numbers. So let's define legs xy to be this colon equal sign means we're just defining legs xy to equal. We're defining legs xy to be the statement x has y legs. So, for example, if we plug in concrete values for x and y, we can get something like legs dog 4 is the statement um, dog has 4 legs, right? So we can have, this is a proposition now, right? So it doesn't necessarily need to be just one variable. It can be as many variables as you want. Now, going back to these quantifiers, these these quantifiers will show up a lot in math, in our proofs, and in everything. So these quantified statements, these quantifiers over predicates are important. You can think of, let's actually discuss each one separately. So let's first go. I gave a little overview or a little introduction, I guess, to what this um, this upside down A and backwards E means. But let's actually get into the details of what it is about. So for all, universal quantification, right? Universal quantifier. So you can think of for all as a generalized and statement. Generalized and clause. So for example, if you're saying for all x in the natural numbers, some property hold, some predicate holds. So let's say q of x is our predicate, right? For all x in n, q of x. Then you are saying, well, this is the same thing as saying q of 1 and q of 2 and q of 3 and so on. I mean, I guess I forgot q of 0 as well. But like, you get the idea. It's just a generalized and statement. And so in order to show that this is true, you have to show that q of 1 is true and q of 2 is true and q of 3 is true and so on. So that's a universal quantification. If you want to show it's false, i.e., if you want to show that not for all x in n, q of x is true, then you have to show the negation of the statement. You have to show not q of 1 and or q of 0 and q of 1 and so on. And if you look back to our previous video where we covered De Morgan's law, De Morgan's laws, remember that the negation of an and clause. So if we have not, let's say A and B, this is the same thing as saying not A or not B. So in order to show that this statement is true, we have to, this is the same thing as saying not q of 0 or not q of 1 or not q of 2 or so on. So that's in order to show that, in order to show that this is true, You just have to show that this not statement holds for any one of these. Now, this has a very interesting relationship with the existential quantifier, which I'll get into in a second. So if we get into the existential quantifier is really a generalized or statement. So if we say exists X in N such that Q of X, and I'm writing X in N, exists X in N. If the domain is clear, if the domain is made clear and it's understood, then we can often omit this is in N notation. We could just write something like exists X such that Q of X. And as long as this domain is made clear. So we have exists X Q of X. This is called the existential quantifier. And you can think of it as a generalized or statement. So exists X Q of X is the same thing as saying Q of 0 or Q of 1 or Q of 2 or so on. So if we want to show that this proposition is true, then we just have to show any one of these is true. If we want to show it's false, i.e., we want to show that not exists X Q of X is true, this is the same thing as showing not Q of 0 or Q of 1 or so on. And so if you look at De Morgan's laws, the other De Morgan's law we have, remember that not A or B is the same thing as not A and not B. So we can write this thing as not Q of 0 and not Q of 1 and so on. So I told you how there's an interesting relationship with this existential and universal quantifier, right? And maybe you might have already guessed it by now. It's that if you look at this negation of not for all X Q of X, that's the same thing as not Q of 0 or not Q of 1 or not Q of 2, etc., right? Well, isn't this the same thing as saying there exists an X such that not Q of X? So we can actually formally write that down as a rule. So we have new rules now with these existential and universal quantifiers. They are really you basically have De Morgan's laws with these existential and universal quantifiers. So if you have for all X, or not, if you have not for all X Qx, then this is the same thing as saying there exists an X such that not Q of X. And similarly, if you have exists X such, or not exists X such that Q of X, that means it's the same thing as saying for all X, not Q of X. And we can actually go over some examples to show why this is the case, right? Let's look at some concrete examples now. Let's get some concrete examples. So, yeah, say that suppose that Q of X was the statement. Suppose that Q of X was, hold on, wait a minute. let's suppose let's let s of x, let's use s. So let s of x be the statement um, x is less than x plus 1, right? X is less than x plus 1. And we want our domain to be, we'll restrict our domain to be the natural numbers again. So x can take on any value from 0, 1, 2, 3, 4, so on to infinity. And suppose we have the proposition for all x, um, for all x, s of x. So we're saying for all x, x is less than 1. Now, is that true or is that false? That is true because no matter what number we take for x, if I choose any number I want from the natural numbers, right? 0, 1, 2, 3, no matter what I choose, it will always be less than itself plus 1, right? So that's how I know that this statement is true. What about the statement, the proposition, exists x, s of x? Is this true or false? This is true because actually this statement implies, this first statement implies this statement. If for, actually, there is some nuance to that. If for all x, s of x holds, then surely you choose any one of those x's, then s of x must hold as well. So exists x that s of x is true. But there is some nuance to this because suppose that our domain is empty. Remember, a set, our domain, it could be, it could have, it could be empty. It could have infinitely many things. It could have, 15 things, but it could be empty. That's the thing, right? So if it's empty, then the universally quantified statement will always hold. So suppose that our domain wasn't the natural numbers; it was just um, it was the empty set, right? It was so the empty set is, you'd write it like this. Then for all x, s of x must hold vacuously. We say it holds vacuously because there is no x to consider. We're saying every x in this set, but there is no x. There is nothing. So this statement would hold trivially. But this exists x, s of x would not hold because there is nothing that exists in that set for s of x to hold. So there is some nuance to that. So long as our domain is not empty, this first statement implies the second. But if our domain is empty, then this first statement is true, but the second statement is not. Yeah. So let's consider another example of predicate. Let's have the predicate R of x, and this can be the statement x is less than 3, and let our domain be the natural numbers again. So if we have the statement for all x, x is less than 3, or for all x, R of x, right? Well, this statement is false because we could choose a natural number 4 such that 4 is not less than 3, right? This statement is false because we can show that this statement is true. We can show for not for all x, R of x, which is the same thing as saying there exists x such that not R of x. And how do we produce such an x? We could just choose 4. And so we have not 4 is less than 3, which is true. What about this statement? Exists x such that x is less than 3. This is a true statement because we can choose x is 0 or 1 or 2. Either one works. So there is some number, some natural number such that this holds. So that's the basics of existential and universal quantifiers and predicates. In the next video, I'll dive more deep into predicates and quantifiers and um, go over using multiple quantifiers. So we don't have to only stick to one quantifier, like for all x or exists x. We can have statements with multiple quantifiers. We could have something like for all x uh, there for all x there exists y uh, such that for all z uh, some statement p of x y uh, and q of z or something like that. We can have multiple quantifiers and these compound predicates with different numbers of variables and so on. We can make this as complicated as we want, but I'll go over that. These are called nested quantifiers right here. I'll go into more detail on that in the next video, and I'll also explain um, how to yeah, I'll go more in detail on that, as well as explain how to like show certain how to translate English statements into, or natural language statements into quantified predicate statements and vice versa. So suppose we had the statement, I think I used this example in my in the in one of the first videos I made on propositions. So the statement, all the dogs in my house speak Latin, or something like that. And I said that this was a true proposition. And the reason for that is because um, so we're saying all the dogs in my house, right? So we can say for all x in and we're saying the dogs in my house. So there's two ways we could write this actually. We could have our domain be the set of all dogs. So for all x in dogs, for all x in dogs, x is in my house implies x speaks Latin. Or we could write it as, for all x in the set of dogs in my house, let DIMH be the set of all dogs in my house, we can say x speaks Latin. And in both these cases, you can see that the statement would be true because, uh, I don't have any dogs in my house. I should have mentioned that. I don't have any dogs in my house. So this implication, because X is in my house, this would be false because there are no dogs in my house. This implication statement automatically becomes true in the first um, in this first proposition. In the second one, well, the set, since there are no dogs in my house, the set of all dogs in my house is empty. And therefore, like in our previous example, this statement is vacuously true. Yeah. So anyway, I'll get into more in depth. I just wanted to introduce predicates and quantifiers in this video, what it meant. I also gave the generalized De Morgan's laws. These laws are important. So and I'll use I'll go into more examples in the next video as well. So thank you for watching, and yeah.